and DNF and all that. On August 11, 2017, I was very, very happy and very, very sad. On the archive was an article posted, a solution of the P versus NP problem by a very reputable professor doctor in Bonn University, Norbert Blum. Very, very respectable. And then we looked at his article, it was nothing obvious. All the critiques about so-called natural proof, how not to tackle the famous P versus NP problem, he explained why all the objections do not apply to his proof. And indeed, it was quite long-standing. It took at least 2 months until he maybe himself found the error. He still promised to post the error on his website, but so far he didn't do it. And so far I think it's still an open problem. What is the actual mistake in his proof? The proof is really a meta-proof. If his argument is right, then somebody that is known to be false would also imply. So it's an indirect refutation of this proof. Nevertheless, it's a beautiful, beautiful article, still worth reading for its own sake. That's because it didn't prove that it didn't answer the $1 million problem. That's because the paper is a little bit erroneous, and doesn't mean it's worthless. So it's very good idea also to know how to write a paper and also how not to write a paper. The word obviously, or it's easily seen, appears there too often. If you want to prove something of $1 million worth, the most important open problems in history, whether P is equal to NP or not equal to NP, you don't have to be afraid to offend the reader and even do the most trivial things. And indeed, some of his paper, I really recommend that you read it. It's a very nice paper. It's still available. That's nice about the archives. Once you submit something, you cannot take it away. You can write a second version, it was wrong. But you cannot, in your own website, you can always pretend you never did it and remove it. So once you got the archive, you take a chance. So he was very, very brave. I really admired Professor Dr. Blum. So of course I was also upset, like everybody else. I was hoping to be the $1 million winner one day. And if he scooped me, I was very upset. But then again, I knew that the chances that I win $1 million is small. And if somebody would get $1 million, I was a very nice candidate for this. Even though he's by no longer a crack. I mean, he's a full professor of computer science at a very, very prestigious University of Bonn. In some sense, he was a little bit an outsider. First, age. And you know the stupid thing that only young people can have breakthrough. He was over 60. So another example that somebody over 60 can still prove a major open problem. So I was rooting for him on his age, because in this sense he was an underdog. Also he was an underdog because he was famous. He was famous for having the record in the so-called Boolean network complexity. So I'm going to explain maybe later, but now let me tell you that the P versus P is not equal to NP. It's enough to find a super polynomial lower bound of blah, blah, blah. So, but it's very, very hard to even prove lower bounds that are much, much trivial. So, the lower bound for whatever, okay, a lower bound of R to the power n log n over. So it has to be a little bit more than polynomial. Polynomial is n to the power 1,000,000. But n to the power log n is super polynomial. So a lower bound of this would give us $1 million. But to get the lower bound of so-called circuit complexity is very, very hard. So O of 2n is not so hard. Then it was the whole thesis in the late 70s to prove 2.5n. And the current record until a few months ago is by the same Norbert Blum. So it was such a big effort just to get peanuts compared to this. So even O of 4n would be a major breakthrough, or definitely O of n to the power 1.0001 would be a major breakthrough. You won't get it in $1, but it's this. And as a guru of computer science that I like as a person, but I don't like him as a computer scientist, Avi Buigdesson, in 1994, he gave a colloquium talk. And when he mentioned about these lower bounds, and he claimed that the best lower bound was O of 4n. And that was erroneous. It's O of 4n for some other unrelated problem. So I wrote an email questioning him. Avi, by the way, in your talk you mentioned O of 3n, O of 4n. And then he answered me a very snide, well, frankly, I don't give a damn. It's just constant. I want a big time. So I call it asymptotic snobbery, because they only care about the long run. And for them it's peanuts. So I was going to write a nasty email to Avi after he would be verified. Aha, the same Norbert Blum in which you dismiss his work as unimportant, is just a constant. He proved the major problem that you were dying to have it. No, guy. So, unfortunately, I didn't have this satisfaction. Maybe Norbert Blum will get another version, and maybe it's still hope. Anyway, so let me describe Norbert Blum's approach. So, a key word is CNF and DNF. So, CNF is also shows up in the formulation of the P versus NP problem. So basically, we have something called algorithms. In algorithm, you have an input, and you have the size of the input. For example, in second grade, you learn how to add two numbers. So you learn an algorithm. The size of the algorithm is not 113, it is 3 in this case, the size of the input. So this is a linear time algorithm. But that's a very sophisticated algorithm, what you learn in second grade. In the old days, 100,000 years ago, the caveman took it and to write 113 marks on the cave, then 123 marks, and then count them together. So that's an example of an exponential time algorithm. And the second grade algorithm is a beautiful linear time algorithm. So some algorithms are exponential, some of them are polynomial. So Cook famously, and Cook Cook et al. And what's his name? Who did the NP? Kamp. Found a whole class of problems that if you can do one of them, you can do all of them. So the grandmother of all NP hard problems was satisfiability. That's for short. So it's really a puzzle. You have n people who tell the truth. So you say, either X1, so either X1 did it, or not, or X3 didn't do it, or X5 did do it. This is the testimony of one witness who is very reliable. Then either X2 did it, or X5 didn't do it, or X9. So such a thing, O, N, is called 3 CNF, because every clause only has 3 terms. Question, if your inputs are the same, can you find an assignment of true and false to make it come true? There is an algorithm. Try all the possibilities. Try all the 2 to the power and possibility. False, true, true. So it is an algorithm, but it is exponential time. Exponential, you have to try to the power up to the power n. Question, can you find it in polynomial time, even n to the power a million? Nobody knows, and if you can do it, you win the $1 million in the positive sense, but probably it's not possible. So it's much more likely that P is not equal to NP. So one way to prove a P with NP is that to take the CNF and prove that a polynomial time algorithm for doing it. But this is And the approach of Blum, beautiful approach, is using CNF and DNF. So it turns out that it's much more convenient to work with an easier problem, the clique problem. So the input are n people. Some people love each other, some people hate each other. Nobody is different each other. Question: can you find k people who mutually all love each other? That's called a clique. So if k is, for example, square root of n, then the n, if you do it by brute force, there is an algorithm. You have to try every subset of n square root of n, see if they all like each other, and eventually you find it. So this is obviously exponential. So the clique problem is really can be written as a Boolean function. Let's see. So by the way, I'm very honored to have Dr. Cheswick, who did the firewall together with this Dr. Sloan here in the front row. So for example, suppose I want to have 3 people who love each other. So one possibility is this Matthew loves. That's your nickname? Yeah. It's close. And Sas loves Neil. And Neil loves Matt. So you do all the combinations. This is with 3, a clique of 3. So it's a Boolean function. So you can write an algorithm. So you want to do a network. So this is called the circuit complexity. You have a Boolean function. So you go to the storeroom. You have 3 components. First you have the not component. That is the opposite. True goes to false. False goes to true. And then you have the or component. And then you have the and components. And of course, the truth table is false or false is false and so on. And here it is, as you know. Now, a Boolean circuit, you have inputs. So in this case, the inputs are all the edges of my graphs. X, n minus 1, x n. So in this case, the n choose 2 input variables. It's really a graph, but it's really loving or hating. So all the scenarios, there are 2 to the power n choose 2. Social dynamics here. Every 2 people can either love each other or hate each other. And then they can start doing things. So you always transcribe it into a network. So you have or, and then not, and then blah, 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 blah. So you have a very, very long. So you go to the storeroom, get lots of components, and components, or components, and not components. And at the end, you have the output. And this is a Boolean circuit. Question is, can you find a Boolean circuit that computes this easily? I mean, let's do this. And make this, and this, so you can simulate the first term, and then do it for each of the 3, and then you have so you can easily construct a Boolean circuit that computes this function. Alas, this has n choose 3, at least n choose 3 gates, and if k is not 3, but square root of n, for example, or even log n, it's exponential. Question: can you do it in polynomial time? In polynomial number of gates. So not time, nice number of gates. So this is equivalent to the NP versus NP. If you can prove that every conceivable Boolean circuit to compute the clique function and then the output requires more than polynomial gates, then you have the $1 million. And that's what Norbert Blum tried to do. But unfortunately, or fortunately, he didn't succeed. So, let me tell you his approach. The approach is really an adaptation of a breakthrough. Oh, by the way, not doesn't count. Not is cheap. Not because not nothing. Only and or are expensive. So, Ransborov, one of my heroes, University of Chicago now, in 1985 came the closest to proving this. He said, if you are not allowed not, if you are not a negative, if you don't like to say no, you always say yes, so only use the component and or, no not, then indeed you need super polynomial time. And this was extended by my friend Doron and Bopana into exponential. So you need, if you're not allowed not, the number of gates required to compute the clique, for example, log n or whatever, square root of n, is exponential. And Rasberov had a beautiful, beautiful approach. Approximate. This is very, very complicated things. So you find, so this is the Boolean lattice on all the graphs. So he found a much simpler lattice. And then he found fake operators. This to mimic intersection, and this to mimic O. So this is much less. So what he had, it did it, and then he took the circuit and translated it into his language, and then said there's something called leftover. You have a leftover when you do it, the real thing versus the fake thing, the approximate thing. This is, and the other one is A fake union minus A real union. The leftovers. And then in the beautiful lemma, he proved that these leftovers are always small. So then he says that the difference, if there would have been a polynomial time thing, there are so many leftovers, there's no way to accommodate it. So that was basically the idea.
What's the square bracket, the square function?
I don't have to know. It's some artificial things that it's a sublattice of everything, so not everything. So you have to go upshoot or downshoot. So it's two upshoots and downshoots. So he had a sublattice that simulates this, and then you get a simple thing, and then as output, he doesn't get the output, he gets something else. But he proves the distance. There are two cases. The distance is such that there's no way, because the lemma is that these guys are always small, so leftovers. So you sum up all the left. So the discrepancy between the fake simulation and the real thing is a combination, is a difference of these individual differences. And each of these individual differences are small. So it was a contradiction. So there's no way. And then somebody whose father is famous, the son of Wolfgang Haken, whose name is Armin Haken, also a very good computer scientist, found another version of Rasberg's proof using CNF and DNF. And then somebody else, Berg and somebody else, found an even better one. So this was the idea of Blum, to adapt the proof of Rasberg using CNF and DNF instead of the original Rasberg one to prove it. And the first step is brilliant. He said, if you have not, I don't like to have not. I don't like to have nots in the storeroom. So put all the negative things at the top. So have x1, x2, xn, and then put once and for all x1 bar, x not x1, not xn. And then thanks to De Morgan, De Morgan says that the negation of x or y is x bar, not x and not y. So with De Morgan, every gate is orbital one. Does not have a mirror gate. It's negative. So you can construct such a gate. You can, from any Boolean sample that has not, you can have this kind of thing, standard. So this part was perfectly okay and ingenious. But then at the end, somehow didn't work, and it did open. So this is the first part of this talk, the sad story, how I could have written nasty email to argue with this one, but so far I have to postpone it. The second part is much older. It goes back to almost 70 years. the icon of number theory and combinatorics, Paul Erdős. I'm very fortunate to have met quite a few times, but unfortunately, I don't have Erdős number 1, I only have Erdős number 2. And this is a shame because I talked to him at least for 10 minutes. And some people only talk to him for 5 minutes and got a paper out of him. That was too timid. And he was very generous in agreeing to be a co-author. And now he's dead. And some people still put his name, but I don't think he's dead. So I have to live with my Erdős number 2, which makes me one of about 5,000 people as opposed to one of 500 people. Anyway, so Paul Erdős came with a beautiful concept. So the problem is in number theory, it was a very nice open problem, never mind the detail, but he has a notion of covering congruences, or covering systems, he calls it. So here's an example. So it's complete number theory. No Boolean function, no circuits, complete pure, good old-fashioned number theory. So you have arithmetical sequence. So 0 mod 2 and 1 mod 2. Then two arithmetical sequences. Between them all, they cover all the integers. So this is an example of a covering system. Very simple one. In general, AI mod mi is a finite collection of congruences or arithmetical sequences. Finite. So A1 plus M1, A1 plus 2 M1, So you have a finite collection of infinite sequences.
Disjoint?
No, not sorry. We'll talk about it in a second. No. This example, disjoint. So if they cover everything, or n, they also this kind of n, then it's a covering system. So that's very boring one. Slightly more interesting is 0 mod 2, 1 mod 4, and 3 mod 4. That's another covering system. And you have many of them. Since there are so many of them, it's nice to distinguish two important subcases. Exact, when there is no overlap. In this case, there is no overlap, the all disjoint. And distinct. By the way, this is joint work with my brilliant student, Anthony Zaleski, a paper coming up in about a month. Exact and distinct. Distinct is a little bit harder. In fact, Erdős was the first one to have a distinct example. Then he put it. Here. 0, nice, historical. And you use it to prove a deep theorem in number theory about primes. It was a beautiful construction. So it's 1950. Good old Paul Erdős. 1 mod 4, 5 mod 6, 7 mod 12. Now, of course, they're not disjoint. 0 mod 2 and 0 mod 3, of course not. 6 belong to both of them, 12. So they're not disjoint. But they're distinct. Every modular only shows up once. 2, 3, 4. So this is much more challenging to construct. This kind. This has a drawback that 12 is not square free. 12 is 3 times 2 squared. Another one that is more interesting, that is square free, is much bigger. 0 mod 2, 0 mod 3, and up to 104 mod 105. So for this, so now they're all square free. There are 14 of them. I don't have time to do it. So that's an example of a distinct, and also all the models are square free. This has a square in it. Here it's 3 times 5 times 7.
Is there any example that AIs are
Sorry?
distinct?
Second?
I mean, is there any example
Yeah.
in which AIs are distinct? Not only MI, but also AI.
Oh, good question. I don't think anybody looked at it. And it's probably not an interesting question, but maybe it is. Yeah, good question. I don't know, and probably. Yeah, probably you could cook up. I would guess you could, but I'm not sure. Good question. So this, and it's 2 years later, he posed 2 problems. One of them turned out to be fairly trivial, in hindsight. Can you have the cake and eat it too? Can you have an exact and distinct things? The answer was no. Not only that, if you write the moduli in weakly increasing order, then the 2 top ones must be the same. So the famous, beautiful theorem that was proved around 1952 by 4 brilliant mathematicians, Donald Newman, Mirsky, Rador, and Davenport. And the proof is the proof from the book. Let me tell you, please, let me tell you the proof, please. I like it, I like it in spite of its many drawbacks. So, look at the individual arithmetic progression, A mod M. And look at the generating function. So this is A plus M, A plus 2M. So add up all the powers. So Z to the power A. So if you look at the sum of the Z to the power of the member, you have a beautiful infinite geometrical progression. So the generating function of a single individual is Z to the power A divided by minus Z to the power M. That's how you call them in generating functions. For example, 1 more 2 is 1 more 2. Matt, what's 1 more 2?
1.
Huh? No, what is the generating function for the sequence? 1, 3, 5.
Oh, sorry. So that's going to be Z over 1 minus Z squared.
Very good. And Anthony, what is the generating function for 3 more 5?
So that would be Z cubed over 1 minus Z to the 5th.
Very good. So since every is disjoint, every integer has to be only covered once. So if you sum them up, this, all the members, you get this identity. And the generating function prime of 1, 2, 3, 4, 5, 6. Oh, sorry, 0, 1, 2, 3, 4, 5 is what?
1 over 1 minus Z.
Right! So you have an identity between 2 functions. And let's separate this into the last 2. And no, last one. Z to the A under Z to the power AN. Now take a primitive root of unity of, Mn. A primitive root of unity does this, omega. Plug it in, take the limit, as equals to infinity. This is finite because it's primitive root, so everything here. But this blows up. Finite plus infinite equals finite contradiction, QED. So this is the proof from the book that Erdős loved so much, and in many, many talks he repeated this proof. One of Erdős' famous, and it's definitely in his book. It's in his book, but not in my book. First it uses analysis, this thing and limit and blah blah blah. You know. To be honest, it's a way to sanitize this and make it not that advanced. You take common denominator, and then it's a polynomial identity, and then you plug it in. You don't have to take limits, so it's still way. But it's still indirect and not very, very appealing for me. A much better proof came in the early 1980s, and 1980s. There was a revolution in covering systems. Sorry, before going on, let me tell you the major order problem. So this first order problem was your exact and these things can live together was very proved